111, a matrix of third order, a squared matrix of third order, each element is 1. We have to prove a to the power n is again a squared matrix of third order, each element being 3 to the power n minus 1. You know, like question 1 of this exercise, this also will be done using the principle of mathematical induction. I have discussed principle of mathematical induction in detail when I was doing question 1. I repeat that will prove that the given statement to be proved is true for n equal to 1. Then we'll let it is true for n equal to k and we'll call it step pk. And if we could prove the result for n equal to k plus 1, we'll say that pk plus 1 is true whenever pk, p1 is true, and hence the statement is true for all natural numbers. This is known as principle of mathematical induction. So I start with the basic step that let us verify that the given statement to be proved is true for n equal to 1. And a equal to this matrix is already given. So to start the proof, I say for n equal to 1, substitute it here in a to the power n. A to the power 1 equal to 3 to the power 1 minus 1, 3 to the power 1 minus 1, 0. So all the steps, all the elements will become 3 to the power 0. And what is the value of 3 to the power 0? 3 to the power 0 on the left you have a equal to 1, 1, 1, 1, 1, which is true. Why? Because this is given. It is already given that A is this squared matrix of order 3. So this is true. This being given, it is true. So we conclude that P1 is true. And now let Pk is true. Pk is true means for n equal to k in the given result, the statement we are letting true. So replace n by k, you get a to the power k equal to a to the power k equal to 3 to the power k minus 1, 3 to the power k minus 1, 3 to the power k minus 1, and so on. All the elements will become 3 to the power k minus 1. Call it 1. And what's our aim? We want to prove pk plus 1. So let me first frame the statement. Now to prove pk plus 1, replacing n by k plus 1, what have you to prove? We have to prove that a to the power k plus 1 will be equal to, if you replace n by k plus 1, because you have 3 to the power n minus 1, so it will be 3 to the power k plus 1 minus 1, that is 3k. Each element should be equal to 3 to the power k. Right? So now, just look at one, pk step. Already on the left side you have a to the power k. If you multiply it again by matrix A, at least the left hand side will become a to the power k plus 1. So the next step is multiplying both sides of pk, that is 1, by a. On the left hand side you already have a to the power k, further write into a to give you a to the power k plus 1. On the right side, better you write a into a to the power k. On the right side also you write a, that is 1, 1, 1, 1, 1, 1, multiplied by a to the power k, which is 3 to the power k minus 1, 3 to the power k minus 1, 3 to the power, and all the elements are 3 to the power k minus 1. So now multiplying, on the left side you get a to the power k plus 1. What about right hand side? On the right side, how do you multiply? You multiply the elements of first row 1, 1, 1 to the elements of first column, that is 3 to the power k minus 1, 3 to the power k minus 1. Multiplying by 1 each, you get 3 to the power k minus 1 plus 3 to the power k minus 1 plus 3 to the power k minus 1. And if you multiply to the second column and third column, you will get the same, and all other elements will likewise be the same, that is 3 to the power k plus 1 k minus 1 added 3 times. So you get 3 to the power k minus 1 added 3 times means 3 times 3 to the power k minus 1, and similarly all rest elements. Now 3 multiplied by 3 to the power k minus 1 will make it what? One power will be added, so we'll make it 3 to the power k, and similarly the other element, which is nothing but the right hand side of the step pk plus 1. So we conclude that pk plus 1 is true whenever pk and p1 is also true. We have proved. So using the principle of mathematical induction, the given statement is true for all n belong to capital N, means for all natural numbers.